We are now going to go into greater detail thinking about the two types of materials we've talked about now, insulators and conductors. Now again, if you've had a lot of chemistry, you might know in greater detail what distinguishes these. We're going to be using a really simple way to think about the distinction. And in particular, we're going to focus on metals. So in an insulator, we know that we have the nucleus surrounded by electrons. And we could classify the electrons into two categories, core electrons and valence electrons. Now what's happening with the valence electrons really determines how charge can move. And in fact, a third category of material is a semiconductor, which we won't talk about in detail in this class, which is different than each of these. But the valence electrons themselves in an insulator are still fairly tightly bound to the nucleus, that electrons aren't able to move from one valence of one atom into another. And for an insulator, this looks somewhat like a crystal in that these are arranged in an orderly fashion, but you can think about these being atoms within molecules as well, and then the molecules are arranged in however. Now, in a metal, on the other hand, you have the nucleus, and you still have some core electrons that are bound, but then the valence electrons are overlapping. They're actually free to move between one nucleus, or ion core, as the figure says, and another. So we call this a sea of electrons. So in a metal, there are an equal number of protons and electrons if it's neutral, but the electrons are kind of free to move around as they please. And so the difference is here, they're bound. They're not able to move, or at least not move very much. We will talk about the caveat here. So when we think about insulators, a lot of insulators include glass, plastic, and rubber. Wood also would be, in general, an insulator. When we think about conductors, we're normally thinking about metals, which is why the focus here is on metals. But a second type of conductor would be something like salt water, so a solution with ions in it. And what I point out is that the body, i.e. the human body, is also a conductor, because we are basically a giant bag of salt water. So we're going to be talking about certain aspects of interacting with charges as literally touching them, and that is assuming that we are conductors. So recognize the reason that we say people are conductors is because we are basically a bag of salt water. So now let's think about what's happening in detail when we are charging our plastic rod. We rub it with the wool, and we've said that the friction is breaking some of those surface molecules such that the positive charges or the positive parts of the broken molecule end up on the wool, and the negative parts of the broken molecule remain in the plastic. Now, the negative charges that stay on the plastic aren't able to just move around. They're in fact stuck there. And so the end that you're holding is still actually neutral. So do think about this, that if you only charge one part of the plastic, that part of the plastic is the only part that is charged. It doesn't just redistribute. The wool also isn't necessarily going to redistribute depending on what it's made out of, but in general the wool is also going to be a insulator as well. Note that the total number of positive charges on the wool surface is going to be equal to the number of excess negative charges, right? We can say excess charges because there's lots of other charges we're not showing, because again, the system started neutral at the beginning. Now we're going to introduce a new concept here, and this is something that can happen in an isolated conductor. So the isolated part matters because later on we're going to have situations where this doesn't happen, but for electrostatics, everything we're thinking about at the beginning of the class, this will in fact occur. So electrostatic equilibrium is the idea that the charges are going to spread out in a conductor until they are equally distributed, and later on we'll talk about exactly how this is defined on the surface. Now, once they are distributed over the surface, we can think of them as being at rest, and that means that there must be no net forces on those charges. So if we touch a metal box with a plastic rod, we transfer some of those negative charges over. And if you say, wait, I thought you said that the charge itself couldn't move, you can think of this as, for instance, electrons themselves, not entire molecules, going from the plastic into the metal, Okay, so that's one way you can think about this, not the entire molecule, just some electrons. Now, initially they would go in only where you're touching, but very, very, very quickly, so quickly we can consider it instantaneous, they would redistribute. We would show it this way, but it's really only on the surface. If this is a solid metal box, we wouldn't say that any of them are on the inside. Right now, this is just being provided to you, but later we will actually be able to mathematically justify why that's going to be true. So they spread out as much as possible, covering the surface evenly, and then are at rest. This process happens so fast that whenever we're talking about an electrostatic situation, we will always go to this final picture called equilibrium, the electrostatic equilibrium, and we're just not going to consider that spreading out process. So now let's think about the discharging experiment that we did previously. The idea being that if you ran your finger over a plastic rod, it would no longer be charged. Now, this is actually going to work with any type of conductor if you have a really big conductor or if it has a path to ground. So let's start with a positively charged object. Now in this case it's metal, but if this was plastic you would have to kind of touch everywhere because the charges couldn't actually move. But in this case, since it's metal, you can just touch one spot and everything can move. So now we see that initially the person is neutral, they're standing on the ground, and the metal's charged positive. Now after they come in contact with this, you see that the positive charges have spread out. So this is the new electrostatic equilibrium. Now remember that positive charges, these aren't just protons floating around, but for instance, some of the electrons from the person went into the metal, leaving behind positively charged ions. You can think about it that way. Now, very little charge is left on the metal object because we've now also distributed it over the person, and in general, the thing you're touching is much smaller than you. What can then happen is a process called grounding, that depending on what the person is standing on, if for instance their bare feet is touching the ground, these charges can then actually distribute to the earth itself. And if you're not aware of it already, the earth is very, very, very big. So you don't actually see a difference when the charge gets then distributed on the earth. It looks like it vanishes, and it doesn't. It's just that the earth is really, really big. So we'll be coming back to a lot of these ideas later, especially the idea of electrostatic equilibrium, but these are really important ideas to understand now as we conceptually start trying to understand things such as using the electroscope.